Hello, everybody, and welcome to the seventh of our HPC Perspectives Live. My name is Sharon Howe, and I'll be your host today as we continue to explore HPC topics. So, throughout this HPC Perspective series, we're hosting a variety of different discussions to introduce you to a number of people across our AI, HPC, and cloud solutions group and industries. We'll get to know them as they share insights of the science behind these latest advances, the teams and technologies that make that happen, and also what to look out for in the future. I hope you enjoyed the most recent episode on life sciences with Gemma from AstraZeneca, one to look out for if you haven't caught that one yet. But today I've got the pleasure to be talking with Nick Heavens from Viridian's Geoscience New Ventures team. He's going to share some insights into climate modelling and the opportunities that AI and HPC can bring into this space in future. Welcome, Nick.
Thank you, Sharon. I'm glad to be here.
Great. So Nick is the Innovation Project Manager for Climate Modelling at Viridian, and you'll previously know Viridian as CGG. So same company, different name. He holds an undergraduate degree in geophysical sciences from the University of Chicago and a master's and PhD in planetary science from Caltech. He's had a very successful academic research career in the USA before coming to work for Viridian in the UK. And that included multiple grants from NASA and NSF in Mars weather and Earth climate modelling topics. He's also the author of 65 peer-reviewed publications, 25 as first author, included a very well-cited short review on climate model development. So, I mean, Nick, that's a phenomenal CV you've got there. But this background in geophysical science, planetary science, is that a conventional background for climate modelling?
I mean, I would say that, it sounds like I've done a lot of things, but I have followed fairly conventional pathways. My undergraduate degree program was a mixture of atmospheric science, oceanography, and hard rock geology. My bachelor's thesis was a really conventional climate topic, looking at interactions between the atmosphere and the ocean of the Red Sea. I think we were trying to understand how to interpret paleoclimate records being derived from corals. At Caltech, my master's research was really about like long-term ocean variability, another rather traditional climate topic. And then I started moving more into planetary science with global modeling of Mars's atmosphere. But I was working in a group that was trying to develop what I would describe as sort of a planet agnostic approach to climate modeling. So we had, we could do a version for Earth, we could do a version for Mars, we could do a version for Venus, we could do a version for Titan. It turns out that it's not quite a plug and play approach, but it did give me a substantial background in things that I ended up doing later. And then my doctoral work focused on Mars atmospheric remote sensing, but it was always aimed at improving what was then the current generation of Mars atmospheric models. And I think my work very much shaped what happened to the next generation of Mars atmospheric models. And then I sort of followed that up. I did a postdoc in, the group, a group of a lead author of one of the Intergovernmental Panel on Climate Change reports, who did very conventional Earth climate modeling, that I was doing something unusual for her. So, yeah, I've done a lot of things. I've gone to exotic places, but, I've always been working a bit with on Earth.
And that sort of Earth and climate has been such a major global topic over the last couple of decades. Throughout your experience, how have you seen that sort of science evolving?
I mean, it's been a massive change. I mean, when I started out, even in the early 2000s, I think people's approaches to climate modeling was it was one of the tools, one of the lines of evidence that was being used for climate sciences to convince the world that we had a problem with human-driven climate change. Then, over the course of my career, people have started to ask more and more, okay, there's only so much that we can do about limiting emissions. what are the consequences of this? How do we deal with the future? And so it's now we're looking at climate modeling as a way of identifying the risks of climate change. And by risk, I mean the possibility that you're going to lose something valuable to you, like your house being flooded so badly that it needs costly repairs and you can't live there for a while, or even that you lose it entirely. And so it's not just like governments or non-governmental organizations that now have to think about the risks of climate change, or individual property owners for that matter. Companies of a certain size in many parts of the world now need to sort of disclose what they're doing, what their risks are to investors, to regulators, just as they would have to disclose, say, a risk. Banks have to disclose the risk of a change in interest rate. Actually, a lot of companies need to, particularly ones that have borrowed a lot, or a cyber attack, or even things like a failure to mature a big technology investment. And so this kind climate is now regarded as sort of a form of non-financial reporting, but people are understanding that it can have material impacts on the financial position of a business. And so they're trying to figure that out. Now, at the leading edge of this problem is insurance, because they specialize in managing and transferring risk to people. And climate change, they think, is a source of increased risk. And as the climate changes, the models they're using to predict risk may need to change, but they're not sure of how to do that, and it's resulting in rather conservative approaches. So there's sometimes having to go to an area and say, we're not going to write policies here anymore because our models aren't working anymore, and we don't know how to fix them. And there's some other sort of regulatory issues of, even if they fix them, it would be hard necessarily to change the premium structure to reflect what those models are saying to them. And so they're just retreating from markets, and that's really negative to consumers. I mean, people want to have homeowners insurance policies, I think, or people want to insure their businesses, but it's going to be bad for insurers in the long run because it's just going to reduce the revenue that they can possibly obtain. But the insurers are right about one thing: the models that we're generally using aren't quite fit for their purpose, because the models we've been using are now getting to the resolution of about a degree. So, for reference, that would treat Los Angeles County in the United States, Yorkshire, all the ridings, or Greater Tokyo area in Japan. All of those three areas would just be single points in one of these models.
So when you're talking about a degree, you're talking about a measurement of distance of the
Yeah,
Earth rather than of
a
temperature.
degree, a
Yeah.
degree. Sorry, a degree of arc. So, 111 kilometers for our, U.S. folks, 60 something miles, 67 miles. And of course, anybody living in a place knows that the weather can be substantially different 67 miles away. Particularly extreme weather events can be different a few hundred meters away, to be honest. Um, and so, because there's so much variability in the potential damage from things like wildfires or thunderstorms or very others adverse events in an area that big, it's challenging to do this kind of modeling. And so, of course, everybody would like higher resolution, but 10 times better resolution, which I'm sure would be a pretty big deal, is an 1,000 times increase in the necessary computing power. And then you have to think to yourself, okay, but you need to make these forecasts for a very, very long time. So weather forecasts, we can do that kind of resolution. We can even do slightly better that resolution. But suddenly imagine having to put that computing power not into a forecast that lasts a week or so, but suddenly it has to last a year, years. It's a big deal. So most of the focus is on using past observations of the weather and then mixing it with these lower resolution climate models to generate high resolution information from low resolution forecasts, something called downscaling. But at the same time, you know better than I do that compute is just getting cheaper and is attracting investments into improving the technology. Governments are investing a lot of money into improving technology, going to things like GPUs, and just creating exascale computers or things on the edge of so-called exascale computing. So we're starting to see high resolution climate models. The question now becomes, can we make models that are high enough in resolution to give the broad market in climate forecasting the information they need at a reasonable cost and at a high enough confidence to make it worthwhile? So
Yeah.
that's me. That's a long spiel from me, but I figured I'd give you an overview like that.
No, that's great. And you were talking about kind of compute becoming sort of more accessible, maybe the kind of cost coming down, but I guess it's also the power of that compute increasing to be able to address some of these challenges as well. So, from the kind of the climate risk part, for the companies to address those risks, they now need to have these kind of climate models or climate risk forecasts for, I'd say, several years, really over the lifetime of their investment, and that they need that the detail that they would get from, I guess, the weather forecast that we see on the news every evening, or we see online, that they kind of to see whether they need to bring their washing in, but they need that for sort of years ahead, and they also need that, I guess, credibility, and within a price that's achieved, affordable, that makes sense against that risk. I mean, that sounds like a really tall order. How reasonably can we predict weather, that far in advance?
Well, the bad news is we can't predict the weather that far in advance. In terms of when we give you a weather forecast, we generally can provide a relatively accurate forecast of how a weather system might evolve over the next few days. Maybe up to a week, maybe up to a couple of weeks, particularly if it's a large scale weather system. If you go to something like a thunderstorm, you might not be able to predict it reliably for more than a few hours ahead. So with climate, we can't work in what is known as deterministic forecasting. We have to work in probabilities. We have to say, well, there is some probability that the weather systems will evolve in this way, some probability that the weather systems will evolve in that way. And when you talk about like statistics over large areas, that's where climate prediction becomes possible. However, we do know that certain types of weather are more likely to happen under certain configurations of the atmosphere and ocean, particularly configurations of the ocean, because the ocean water has a high heat capacity and effectively it's said to have a memory uh, um, that allows it to sort of store something that influences weather conditions for a long time. So we have phenomena like El Nino or La Nina, or more obscure things like the Atlantic multidecadal oscillation, that depending on what particular phase these things are in, you can get much different types of weather. So we can't predict necessarily that a hurricane is going to hit Houston a year from now. What we can do is say Houston will have an increased risk of a hurricane a year from now relative to some historical background, or a decreased risk. We don't know. Every year is different. But that's sort of that's where I think climate prediction can go. And we're starting to see that come out of a variety of both academic researchers and companies trying to provide products along those lines.
That's yeah, sounds interesting, and I'd like to our audience to understand a little bit more about the complexity of what a climate model looks like. Could you walk us through a typical climate model and the process that's involved, please, Nick?
Oh, how long do you have? No, no, no.
Well,
We have only so much time, but I'll keep it as simple as I can. The type of climate model that we usually hear about is often termed full complexity because we're covering three dimensions in space and we're trying to simulate the movement of a fluid like air or water somewhat directly, though, of course, at some resolution. Such a model is divided into components for different parts of the climate system. So you'll have one model that might run the atmosphere, you have one model component that might run the ocean, one that might take parts of the land, though sometimes this is all sort of something we sometimes merge things. Often from sort of a software perspective, it's useful to do some things in certain ways. But the concept of a component is always there because we're always thinking about how they're exchanging energy and material between the different components. The atmosphere and ocean are modeled by solving a particular form or some particular form. It's not always quite the same solution concept of the Navier-Stokes equations for fluid motion. A large part of the energy of the fluid motions is not going to be resolved at the resolution of these models. So the model needs to estimate these unresolved processes from what it knows about the motions it's actually resolving. This is referred to as parameterization. So the parameter in this case is what you know about the flow at the resolution you have. Of course, the components are exchanging information, as I said. An example might be the wind is blowing on the top of the ocean, which results in some momentum exchanges or some heat exchanges. So a component called the coupler manages these exchanges. So that is like, the one paragraph introduction to how a climate model works.
And so this is really where the HPC part comes in. This solving these forms of the Navier-Stokes equations is really where the challenge lays.
Uh,
And and
Yeah, I
these
mean, it compute one of the motivations for developing early digital computers was weather forecasting because L.F. Richardson in about the early 1920s had the idea of basically starting to run weather models in the form of something like a symphony orchestra. He imagined having a bunch of people with pencil and paper in a room, who knows how many, and then somebody like a conductor kind of guiding them through the calculations. Of course, this is a ludicrously impractical idea, but really, HPC is really Richardson's orchestra, just translated to a lot of electronic components.
and I guess we're not writing code on pieces of paper anymore, but what language are we using now for that code?
Okay, so this is everybody thinks that I'm like from some sort of former age when I talk about this, Fortran, but Fortran 9095 or later standards is very popular. We're usually using some C preprocessor directives and a lot of C library support for some functions because that just really speeds things up. There have been some attempts to create like a Python-based climate model or even a Julia-based climate model. There's certainly some aspects where, particularly if you do a good deal of C bindings on the Python, maybe that actually can be equivalent. And it certainly has intelligibility advantages sometimes. And Julia, I don't know enough about Julia to say how well it does, but I have seen some really good work with atmospheric chemical models. So it's possible that people will start sticking in certain things that Julia works better for into conventional climate models. But I don't really see a whole Julia-based climate model being popular at the moment.
And are we talking about massively parallelized code as well?
Oh yes, yes. I mean, you need MPI with interconnect that is now in the hundreds of gigabits. To give you an idea, a 1 degree model runs through a century in about ooh, 16 days, I think, on about 720 Intel cores. So if you wanted 10 times better resolution, you start talking about either very long time to solution or an impractically large number of cores because you can only divide the problem so far without the interconnect just taking it all up. And it's thought that really some important processes, if you really wanted to resolve them, you could only resolve them at maybe 100 meters or maybe 280 meters is one number I've seen. So even like 1 kilometer, you're only resolving half the energy, which just results in physically impossible resource needs. A million times, a billion times. It's just not going to happen.
So I know I didn't mention this when I first introduced you, but we're probably at the time when I should shout out that you are developing a high resolution climate model for Viridian. So there's a lot of research going on in different areas. What makes what you're doing different?
I would say, oddly enough, that what I'm doing is in some ways relatively mainstream. I'm just trying to take the latest research about how we make models at high resolution, but how we would take something like the classic climate model used for predicting future climate change over a century that's running at this 110 kilometers or whatever. I'm trying to just figure out how do we bring that globally to much finer resolution, 15 kilometers, 3 kilometers in a limited area even, but with a consistent, global resolution model surrounding it. Um, so I start with a weather model called MPAS-A, the model for prediction across scales, which is a global implementation of the very well-known weather research and forecasting model. And in fact, that's what WRF development will become. If you know anything about WRF, that is going to be focused on this MPAS, which is the other acronym for model for prediction across scales. And this is widely used in weather research. So starting with a weather model to build a climate model is unusual once, but it's now much more popular. So for instance, the European EC Earth model starts with the European Center for Medium Range Weather Forecasting, or you may have heard them as ECMWF. They have their, what is it, integrated forecasting system? Yeah, IFS. Um, and so that's the basis for EC Earth. I think there's a couple of other models now. They're using sort of weather models as their atmospheric component. And then it's really off the shelf parts. I take a popular European ocean model, an American wave model for the other components, and amazingly, a very flexible coupler that has some American heritage but is mainly done in France these days. And all of these models are used widely and documented in the scientific literature. So again, it feels like it's original, but it doesn't feel like I'm going off the deep end anywhere. But combining these particular elements is just unique to Viridian. And as much as it's possible, I'm just trolling the literature and finding how are people basically improving how these models function at high resolution. I'm putting in the kinds of things that I can do to work, trying to again meet the standards for a CMIP model, particularly about properly reconstructing global energy balance and the different components of it, how much clouds are reflecting, how much they're absorbing, as all sorts of things like that as much as possible. Um, and it's just again, it's all about meeting the same evaluation criteria I'd use for a low resolution model. Um, so one thing you can do with that is, for instance, you can configure the ocean component to have a realistic response to a disturbance. So one classic thing is if you have a tropical cyclone moving over the ocean, it stirs up the waters. It brings up cooler waters from beneath. So what I can do is I can put in something that says, actually, I'm not going to keep the sea surface temperatures fixed at some single value. What I can do is I can say, well, if it's disturbed from a single value, just relax it back over a period that would be realistic for relaxation in the real ocean. So it's a conventional model. It's what I want to use it for is key. Nobody is providing this kind of resolution for seasonal forecasting, but insurers, real estate investors, companies with a lot of physical assets may need to want to know what the year ahead looks like for risk modeling, for underwriting, for determining how many spare whatchamacallits they need to repair something if they get hit by adverse weather. Um, and so this model is designed to actually produce these seasonal outlooks that are not being provided by anyone at the moment at the kind of resolution that we're going for. And I mean, really, in the end, I want to give businesses climate modeling that's credible as what academics or government labs would make, but provide it with the resources that are always going to be beyond academics, but also give the focused client attention that a public weather climate services agency generally can't provide.
No, that's it's all fascinating. Are you able to share anything from your model?
Yeah, I got a
Should we try this
couple of fun
animation?
slides. Yeah, let's
Yeah,
do a
let's try
couple of,
it.
let's see. Gonna have to do, yeah. So we'll put slideshow on. So what we're looking at is an animation. I basically filtered out all the non-damaging winds. So the sort of the blues and greens are sort of lightly damaging winds. And then if you get yellows, you get to something that's more like hurricane force. So this is showing a variety of systems, but a lot of them are tropical cyclones, including about a category 3 hurricane that moves. And I'll just go through the animation again. It's going to develop again in a couple of more frames, but let's see, just it's worth waiting. Okay, so you see it comes off the Cape Verde Islands, off the coast of Africa. It's moving. It isn't developing a huge amount. It's now going sort of north of the Leeward and Windward Islands towards the Bahamas, going through the Bahamas fairly slowly, goes through the coast of, goes over Florida, actually strengthens a bit in the Gulf of Mexico, and then comes in somewhere near Texas, Louisiana border. And you see a few other weaker tropical cyclones in both the Pacific and the Atlantic in this particular one. But this isn't a weather forecast. This is actually just in the middle of a year-long climate model simulation, starting with initial conditions in 2023. So this isn't what actually happened in 2023, but this is an idea of a possibility for what would have been consistent with the conditions in 2023. It's the basis for the kind of probabilistic modeling that we can do. We can just do about 30 of these and get an idea of the possible range of what could happen. And then a lot of data analytics that you can do here. And one of the things we do is just pull out, what do the tropical cyclones look like? And so the colors show tropical cyclone intensity. And so you see that storm that I showed you, though actually it's ended up being split into two systems because it weakens at a certain point and then redevelops. Um, but you get an idea. This is at 24 kilometers. We're actually aiming to go a little higher resolution because we will actually be able to get intensities, or at least a proxy for intensity, a bit better. But the idea is we can just extract real systems from the real types of systems from a climate model. So we can actually talk in terms of actual weather events instead of like the mean temperature in July, which is what you typically hear when you're talking about climate models.
Okay, no, thanks for sharing that, Nick. That's impressive. You talked there about going to even higher resolution. Now, from a compute background, I can only imagine that you mentioned before how that's just going to kind of increase the computational load. Um, I can see that you can save on that computation by a variable grid resolution. You maybe not need the resolution in certain areas or others. Um, but is that really enough? How can we bring that down? What else can we do to support that?
Yeah, it's a great question. We're rather fortunate that CPUs still seem to be getting better and cheaper. It's sort of amazing. I had a friend at Cornell many years ago who was working in the area of like processor development for his graduate program, and he was getting extremely frustrated. He felt like we're going to hit a wall in 3 years, and I'm not going to have a job. So if I go into industry, it's just going to be terrible. It turns out that I think he was overly pessimistic. But CPUs are not going to be able to fill all of the gaps. So there's going to be a couple of two. There are going to be a couple of classes of techniques that I think are going to help us bridge the gap. Code machine optimization is a big deal, as well as offloading to graphical processing units. At the moment, we build code quite generally for a wide variety of processor architectures. I suppose the analogy is to think of knowing many words in the language, but not knowing the name of a specific object, like, oh, celery. So you spend time rambling on about the long, the green, the spongy, the crunchy, the watery plant that you eat with your favorite dip instead of celery. So we need to figure out ways to make the program speak more idiomatically with the machine so instructions are more efficiently given and received. The easier to understand example is offloading to GPUs. GPUs are just really energy efficient ways of doing math. You know, they have some limitations in memory and information exchange, but to be honest, for the types of applications we have, those as GPUs, the last few 2 3 years, GPUs have now gotten to the point where I'm not worried about, for instance, information exchange, because it's gotten comparable to InfiniBand interconnect sometimes, the kinds of throughput. Actually, it's better now. An H100 is something like 1,500 gigabytes per second. For the kinds of things that we're doing, that's I mean, it may be gigabaud, but the point is it's really really fast, um, and they're really good at running through loops, which are quite common in parameterizations and climate models. So, I mean, when I was initially thinking about this, I was like, have they really lived up to their promise in this area? And I think maybe in the next year we will see a couple of major developments where they will. Maybe Viridian will be doing it. Maybe there's somebody at NCAR or Colorado States who will be doing it. But I think we're about to see a major leap in what we can do with GPU offloading with climate models. Um, the big issue is just reproducing mathematical operations on CPU in the GPU framework, which leads to consistency issues when you're trying to understand, like, why is this running differently on a GPU than a CPU. But even that, I think as we go more to looking at single and mixed precision programming, we're going to find that a lot of that goes away because we're going to be doing things a little bit more the way we're doing on GPU.
We certainly manage at Viridian to use GPUs very effectively for many applications, particularly in sort of seismic processing and imaging. And we've been doing that for a long, long time. We can run significant amounts of work on GPU very effectively. So it's interesting to see that usage spreading more widely potentially.
Yeah, I mean, and I always like saying that Viridian was working with GPUs before there were programming languages for GPUs. It's a nice line, and I have checked it out. It is accurate. Um, this wealth of experience that the company has opens up some new options that haven't been tried by the academic and government research communities that have been trying to put climate models on GPUs. So, I'm giving it away. We're working on this problem. So if you're one of our academic government competitors on the webinar, there may be, I think there might be one or two online. Yes, we're competing with you, but it's friendly competition. We hope to figure out ways of sharing our knowledge.
And I guess one of the things with the GPUs and one of the things that we bring from I guess our long history with running scientific algorithms on compute is that optimization piece. We're a commercial company, so we talk a lot about that topic, whether it's on the kind of the application end, on the hardware end, on the infrastructure end. Um, for your climate modeling, are there particular aspects of the workflow or implementation that are interesting for the optimization of climate models?
Yeah, I mean, the topic that gets batted around in climate modeling at the moment is, as I mentioned before, sort of the question of precision.
Mm.
So we've spent a lot of time in climate models just just programming with double precision reals, so 8 bytes or 64 bits in computer memory. Um, what this means is sometimes we create these excessively precise calculations and waste compute that way. So there's been a lot of thinking of, can we go to single precision, mixed precisions, even like a quarter of the size, so going to like 2-bit real or 2-byte reals for certain purposes. Um, and when it comes to GPUs, they can do matrix multiplication extremely efficiently with smaller precision variables, and then there are ways of basically storing the more refined results at better precision. Um, a- and this is, I mean, this is great. There's major savings in power, memory, time to solution this way, and that's just the part that I know about where I can understand what's going on. I definitely talk with the teams that work with you, Sharon, and they tell me about things that are just beyond my understanding. I just have to say that, like, it's almost, a, a certain level of sophistication is indistinguishable from magic. So there's probably several other areas of optimization that I'm not considering, but it's certainly precision is one. Yeah, I understand that if I'm messing around with smaller sets of blocks, then it should be easier than if I'm like, carrying concrete blocks around trying to do calculations.
No, it's great, great topic. So, what really is the future we're looking at? What do you really see happening, Nick? Are those climate models going to go to 1 kilometer globally to 100 meters? We're stretching the limits, but where is that value point for companies in terms of the risks that they're facing and the information that they need?
I think you're going to find that academic government researchers are going to do some limited experiments at these excessively high resolution. Well, I'm not going to call them excessively high resolutions. At resolutions that actually resolve many of the processes, not all the processes, but many of the processes. So maybe that you will see a 280-meter resolution simulation, but in order to actually run these practically as climate models, even for purposes of reports for the UN or whatever, we're going to hit a practical resolution limit soon. It's probably between about 1 and 10 kilometers. So processes will still need to be parameterized, including, to be honest, microphysics. I mean, it has the word micro in it, so it does seem to be small. Is really like, how do things form in clouds? How do clouds form? How do droplets form? How do little bits of ice? How does hail form? All of that is just always going to be below the scale. So there's always going to be a need for parameterizations. But I think for companies, being stuck between 1 and 10 kilometers is not such a bad thing. At a certain resolution, a probabilistic forecast is more about the setting than the weather. So, for instance, if you're worried about flooding, you a thunderstorm could happen here, a thunderstorm could happen there, but it all goes in the same watershed. So it's a matter of where you are relative to that watershed. If you're Gatwick Airport and you have a little river by you at all times, it doesn't really matter if there's a thunderstorm in Horley or if there's a thunderstorm over the airport itself. There's a pretty strong chance that if there's a lot of rainfall, that little river next to Gatwick comes out of its banks. That's just the way it goes. So I think that really that 3 kilometer scale in terms of understanding the atmosphere will be revolutionary, will be sufficient for business decisions. What they will have to put in, as people are putting in now for a variety of purposes, is understanding the land surface for flooding, understanding vegetation for doing wildfire modeling. So there will be some added sort of small scale components, but they won't have to have atmospheric information at really, really, really high resolution. So probabilistic climate forecasts at the scale of an office building are almost certainly going to be overkill. And we're working on ways of basically building large ensembles of information from small ensembles that we get out of a climate model. which is a series of extremely computationally efficient mathematical techniques. It's called like stochastic event generation in the insurance catastrophe risk modeling industry. So that's relatively simple. But the future, I think, is very much about machine learning. At the moment, most of that is about training algorithms to emulate the integrated behavior of weather forecast models, or maybe to do some climate model downscaling. Um, but there's an argument to be made. An old professor of mine, Tapio Schneider, and his collaborator, Ruby Lung, the lead climate modeler at the US Department of Energy. So they just argue that parameterizations are a better target for machine learning training and emulation. And I'm every once in a while, I will definitely be seeing a paper where they're doing this, because parameterizations are really physical models within the larger climate model that depend entirely usually on local information in the vertical. That is, they're just a big column. Well, you might be able to just train an algorithm to capture that behavior, particularly those microphysics problems I was mentioning. And that might be able to take away at least a quarter of the compute load. Much of the rest of the load is just integrating Navier-Stokes. So if you could emulate that, you could imagine creating climate models that are sort of a mix of interlocking machine learning algorithms that have some input-output mediated by a coupler. We're probably a bit far from that, but I say that, and then every day I see a paper that feels, oh, we're getting closer, or somebody will release some code and I'll say, oh, we're getting closer. But I just like to say that I think the kind of work that we're doing with high resolution climate modeling is sort of the beginning there, because it's allowing us to see, how do you evaluate a model like this? If you built a machine learning model like this, how would you evaluate? How would you say we can actually trust these results?
Yeah, and that trustability helps build that credibility as well, I guess, then. So, now thanks for explaining that. And I think on that topic of risk, when you were talking about then the additional data sources that are maybe needed to build that full picture for companies, that makes that field very collaborative, um, with lots of information from lots of different disciplines coming together.
Yes. So one area that you know could become important at some point is subsidence. So the brass tacks part of it is, your house may be on a geological structure that is sensitive to big soil moisture changes. So the classic example is swelling clays. If you're on clay that it can accommodate water within its structure, if you have a drought, suddenly those swelling clays start losing their water and they just compress in volume. And if your house foundation is on those clays, well, your house sinks. And maybe not just straight down. And that will damage foundations. They may damage aspects of your structure. In the UK, it's like a 350 million pound a year problem sometimes. Particularly 2022, we had a particularly bad high heat wave, temporary seasonal drought. So a lot of soil moisture being pulled to the ground. A lot of areas around London, clay, a lot of claims. So it's that kind of information that can go into these models of risk, as well as this sort of larger scale atmospheric information. And you can look at it in terms of like the background bedrock geology, or you could measure it from space. And so a few years ago, actually, we were working, Veridian was working with a few partners on understanding how to measure subsidence from space. So, hey, that's something we could do again. So, if anybody's interested, come talk to us.
Uh, Thanks, Nick. So I guess to finish with, I'm conscious of time actually. We've got huge amounts of exciting developments in this space. What for you, what's happening either now or in the near term that really excites you?
Every day it seems like there's something new in AI weather forecasting that I just go, wow. I mean, today was an especially big wow. A few people in the National Severe Storms Laboratory in Norman came out with at least a preprint today where they've taken a short-term severe weather prediction model. So something that is designed to sort of predict thunderstorms over the United States in a concentrated area, but a very high resolution. And they've got a machine learning algorithm on a GPU in a few seconds to just evolve something that does slightly better than that model you know, at 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 two, for a couple of hours. Maybe it smooths out the extremes more than you would like, but that kind of thing can actually just allow you to look for little sensitivity changes and actually see like what is the effect of your assumptions on predicting the path of a thunderstorm complex in the next couple of hours. So for warning the public, that's really, really useful. And the idea that you won't have to spend a huge amount of computational power to do that makes it possible for someone in an individual weather forecast office to run an algorithm, get an idea of what's going on, and just to make hopefully better warnings that give the public more accurate information about what's going on and save people's lives. Nothing better than that in meteorology.
No, absolutely. Well, thank you so much for joining us today, Nick. We've done a bit of a whistle stop tour through, I guess, through kind of climate. We've gone through physics, fluid dynamics, touched on a bit of geology. It's a wonderful combination, and obviously, we've seen what the power of computing can drive in terms of those developments into the future. So I'm super excited to see what the future developments that are coming out of your team. So yeah, thank you so much for joining us today, and thank you so much to everyone who's joined the live stream or are going to join the recording of this. If you've got questions for us, then feel free to reach out. Nick's really active on LinkedIn, so do give him a follow on there as well, and let us know. Otherwise, take care, and hopefully we'll see you next time. Thank you for joining.
Thanks very much. Thank you all for listening to us.